Hello again. In our last video, we talked about using cosine similarity to do a semantic search. So in practice, that means that we embed some text, let's say a user's query, and then we do a search for looking for comparisons between that user's query and embedded text in some sort of document store. So in our toy example, I was using AI Karl Popper, philosopher Karl Popper, and imagine that we're going to do a query, maybe something like, what is your opinion of induction? So Karl Popper wrote quite a bit about induction and had a very negative opinion of it. So we would take the user's query, what is your opinion of induction? We would embed that into a semantic space, into a vector, and then we would have maybe already have taken every single thing that Karl Popper's ever written, broken it up by paragraph, and embedded each paragraph. And then we're looking for the most similar matches between the user's query and the writings of Karl Popper. So now, obviously, by doing this, it's not just doing a lexical search. It's not just looking for specific words. It's looking for semantically similar concepts. So it's going to be looking for the word induction or something similar to that conceptually, and then it'll be looking for places where opinions are being expressed. Now, you can actually do a combination where you do a lexical search and a semantic search, a best of both worlds approach. But this is obviously a semantic search using cosine similarity is obviously a really useful tool in the toolbox to be able to search through large bodies of text like this. Now, we did bump into a problem. Specifically, cosine similarity is very slow. We have to first embed the user's query, and then let's assume that we've already embedded all of the paragraphs, paragraph by paragraph, of the writings of Karl Popper. Then we would still have to take that vector that we've created out of the user's query, and we would have to do a cosine similarity against every single paragraph that he's ever written. And of course, he's written a ton of books. And we could imagine even in some sort of industrial data store here that maybe has hundreds or thousands or even hundreds of thousands of books. It could get very, very large, and it could really make this a painfully slow process. So how are we going to deal with that? So that's what we're going to talk about in this video today. We're going to use an approach called Hierarchical Navigable Small Worlds, or it's usually abbreviated HNSW for short. So how does HNSW work? Well, there is a groundbreaking paper that's on the subject called Efficient and Robust Approximate Nearest Neighbor Search Using Hierarchical Navigable Small World Graphs. It's available out on Archive. It's a very famous paper. It shouldn't be too hard to look up, and it's available for free. It was written by these guys, Malkov and Yashinin. So how does it actually work? Well, let's start with the idea of the k-nearest neighbor algorithm, which is a very famous and very old machine learning algorithm. Basically, the idea of the k-nearest neighbor algorithm is that you're given a new instance, that's our green circle here, and we want to classify it. It either needs to be a red triangle or a blue square. So to do it, we look inside the hyperdimensional space in which it exists. Obviously, this is going to be, maybe thousands of dimensions. I'm just doing it as 2 dimensions to make it easy to understand. And we're going to say, okay, maybe we say we want to classify it based on the 3 nearest neighbors. In this case, if we were to do that, that would be this circle. There are 2 red triangles, 1 blue square. So this would then become a red triangle. Or we could say 5 nearest neighbors. That would be this circle there, in which case it becomes a blue square. So the idea, though, is that you are trying to classify a new instance based on how close they are within some sort of vector space to each other. And you're looking at the neighbors that are the closest to it to determine what the new classification is. Now, we're not doing k-nearest neighbor when we're doing HNSW, but conceptually there's some similarities, and a number of the optimizations that came out of k-nearest neighbor were used for hierarchical small worlds, hierarchical navigable small world. So imagine that instead of having just a giant database listing of every single paragraph of a book, in this case with my toy example, that would be AI Karl Popper, so every paragraph he has ever written. Instead of having all of them and then checking against every single one with a cosine similarity, what we're going to do is we're going to put it into a graph. So imagine you're entering here. This is your first node. So you would then start to look into the neighbors of that node, and you would see if those neighbors are closer or further away semantically from the from the query, the user's query that you're trying to compare it to. If it's closer, then you move to those nodes. You continue your search until you arrive at a node that no matter which direction you move, you are further away from the user's query, the embedding of the user's query. That is then your hit. That is the closest one that you're going to find inside this graph as far as cosine similarity. Now, that's part of the trick here, is that we put it into a graph. Graph theory is something that has been around a lot longer than even computer science. It's a huge part of computer science. We've got a lot of understandings about what you can do with graphs and how to traverse them. So the fact that they put this into a graph is a really useful thing. And just the very fact that it's in a graph makes it so that it's easier to move around. You don't have to search everything. You can just search certain nodes. But even this would still be quite slow. So let's imagine that we're going to take this graph here and let's make that just the bottom layer. Okay. And let's imagine putting a graph on top of it. Smaller graph though. So you come in here now and you search around, you find this node, and then you drop down from the coarse grain graph to a more fine grained one, and then you continue the search until you find your closest hit. We can even imagine doing this in more than 2 layers. So we're going to come in here, we're going to drop down, etc. And by doing this, you would end up with a fairly quick search. However, it comes at a price. The price is that you're only an approximate nearest neighbor search at this point. So you aren't going to get the exact closest best cosine similarity. You're going to find the some approximate ones. It may not be the exact best one. So you're losing something, but you're gaining something, namely that it's going to work at a much, much faster pace. By the way, all these come straight out of the paper that we're talking about, Malkoff's paper. So you can look at that, and I'm just basically stealing the graphs right out of his paper. Okay, so now something else that came out of their paper was this heuristic. So if you've got clusters in the graph, we want to be able to not force the person to have to go all the way around to get to a cluster that's actually the right one for them. So they have a heuristic that allows the clusters to be connected and to draw a link between nodes in clusters. And that helps us guarantee that you will end up with an approximate nearest neighbor hit if you're using this algorithm. So how do we actually do this in real life? Well, in real life, the good news is that there are existing databases that will build an HNSW index on top of a normal database and that can store vectors. So for example, the popular PostgreSQL database, it does not come native with the ability to do vectors and an HNSW index, but there are modules that exist, one called pgvector, that you can then install as a module on top of PostgreSQL, and it gives it that additional functionality. So the first thing that we're going to have to do is we're going to have to install PostgreSQL, and then we're going to have to install pgvector, the module that gives us the additional functionality. Now, the easiest way to go about this is probably to look up my blog post. That's the URL you see on the screen, and to follow there. I'm not going to go through all the details in a video. There's just too much, really, and for most people, it's probably not necessary. But let me just get you started here. What you're really going to want to do is you want to start by going off to postgresql.org, and from there, you're going to look for that download button. Here, let me actually show you just the first few steps of making this work. So here's the home page. I'm going to click on download. In my case, I'm going to go to Windows. And then I'm looking for this download the installer. I wish they hadn't buried this so far. It's a little annoying that they did that. And then you come into here, and we're going to, since I'm looking for Windows, I want to get the latest version, 17.4. We've got Windows. There's only the 64-bit version. There is no 32-bit version. I click here, and it's going to take me to this page, and it will actually then start the download. So I'm going to now click this. You can see that I've got the PostgreSQL 17.4 for Windows 64-bit. So you're going to then download that, and that's actually how you get started. And most of this, you can just follow the installer as far as installing PostgreSQL. Now, the hardest part here is actually installing pgvector. So if you go to github.com/pgvector/pgvector, that's actually where you want to start. They've got installation instructions here. Most people probably listening to this video will be able to just follow those instructions. It's a little bit complicated, so I will make a separate video just showing how to install pgvector. Just to help make sure that you can get through this. But you don't have to wait for that video. You can go directly to this link and you should be able to follow the instructions. They've got Windows, they've got Linux and Mac, and you can then add pgvector as an extension into PostgreSQL. And once that's set up, then you have got the ability to start using HNSW indexes and vector search to do a vector search and to have tables that contain vector fields. And this will allow you to do a approximate cosine similarity across a very, very large database of documents. Now, what do we do about the fact that it is approximate? Well, there's actually some tricks that we're going to learn in a future video that will allow us to try to still find the strongest hits, even if we're only getting back approximate hits out of PostgreSQL. Well, that's it for this video. Please don't forget to like and subscribe, and tune in next time and we will talk about how to install pgvector, and then we'll move on to how to actually use all this to build an application that uses cosine similarity, semantic search, and large language models.